Assalamualaikum warahmatullahi wabarakatuh and good evening to TS Dr. Saiful Rizal bin Masrul. Today, our group from Group 1 to present about double tube counterflow heat exchanger. Okay, this is the my group member. First, Ahmad Shafawi bin Ferus, Nobometric CD240145. Second, Muhammad Shahrin bin Nordin, Nobometrics DD220110, and it's me, Muhammad Fahmi bin Farul Razi, Nobometrics DD230014. And lastly is the Cairo Azri Amir bin Minat, Nobometrics CD230317. Okay, this is the our contest for the presentation. First, the project background for the project. Second, theory and method. Result, discussion, conclusion, and the recommendation.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Syahrin bin Nordin. My metric number is DD220110. Okay, now I want to bring all of you to my presentation about project background. All right. A double tube counterflow heat exchanger is an efficient system for transferring heat between two fluids moving in opposite direction. That's mean or point A to point B. All right. Uh, is comparison to concentric tube with one fluid flowing through a inner tube and the other through is in the other through the outer tube. The counterflow design maximize the temperature difference across the exchanger, boosting heat transfer efficiency. Commonly used in power generation, chemical processing, HVAC, or HVAC is mean heat ventilation and air conditioning, and refrigeration. This type of heat exchanger is valid for its simplicity, ease of maintenance, and reliability. This project focused on designing, evaluating, uh, and optimizing the heat exchanger to achieve maximum thermal efficiency and contribute to energy saving, reduce cost, and increase sustainability. All right, we go to objective. There are three objectives of this project. That means our group get three objectives for our project. Number one is design optimizing. It means the aim of the design is to realize an effective double tube counter flow heat exchanger by selecting proper material, dimension, and configuration that will maximize thermal efficiency and minimize pressure drop. It means what design we want to choose, what material we want to use to achieve our machine or our objective. Okay. Number two, performance evaluating. It means the performance of the heat exchanger will be evaluated for a wide range of operating condition regarding flow rates, fluid properties, and temperature range. Uh, Pinpointing the most influential factor and efficiency and effective. That means how the material perform and uh, how can the material can achieve our mission objective. Okay, now we go to the third point. in our objective is sensibility and cost effectiveness. It means establish the potential to realize energy saving, cost reduction, and environmental sustainability upon improving design and operation for industrial application involving a double tube contact flow heat exchanger. That means how the industrial how the industrial achieve their objective. That means they want a lower cost but a higher profit. How they want to make this mission to complete. Ah, okay. Another example that I can give to you is they want the the cost. They want to reduce the cost and the profit. They want to sustainable the profit. How want to they want to survive in our millennium. Okay, that's of my point. Thank you.
Okay, now I will present about theory and method part. So, heat exchanger is a device that primarily used uh, within process industry to transfer between two fluid, commonly hot fluid and cold fluid. So, the common type of fluid is including wall tubes or flat or curved surface that separate between hot and cool fluid. So the convection transfer heat from the hot fluid to the tube wall or plate, then it go to the cold fluid. So in this project, uh, the heat the type of heat exchanger that we choose is uh, counterflow double tube type. So where the fluid enter and exit through opposite ends and circulate in opposite direction. So to improve this, the heat exchanger, there are several factors that we need to consider, which is the first one is heat transfer coefficient, temperature difference, and heat exchanger area. So to maximize the efficiency of the heat exchanger, we need to consider these three tips, these three factors, to make sure that the heat exchanger running in the most efficient way. So next we go to the step of analysis. So this is our step analysis. The first one is problem identification, which is in this question we need to determine the overall heat transfer coefficient of the heat exchanger. And then the data collection, which is we need to gather all information on the heat exchanger, such as the tube diameter, flow rate, temperature, type of liquid that involved in this problem, and also the surrounding environmental factor. Next is to find the heat transfer coefficient, which is to liquid in this question is oil and water. So the first one we need to identify the properties of the water, which is in the table A9 in book, and also temperature liquid property for oil, which is in table A13. And after we identify all the properties, we calculate the question using a Reynolds number and also Nusselt number. And then after that we should be get the heat transfer coefficient for water and oil liquid, and then we can calculate the uh, overall heat transfer coefficient, and then develop solution. After, as I said just now, after we get the heat transfer coefficient for oil and water, then we can calculate overall heat transfer coefficient. So last one is improvement solution, which is uh, solution that how we want to improve the the heat exchanger by changing any related properties and adding four factor improvement problems. Now, thank you. I will pass to next presenter.
Problem example with solution. This calculation show how to do design for double pipe heat exchanger and estimate length of double pipe required. Determine heat load, obtain flow rate, inlet-outlet temperature and fouling factor for both hot and cold stream. Calculate physical properties like density, viscosity, specific heats, and thermal conductivity. At mean temperature, determine heat load by energy balance on flow streams. In this equation, where mass flow rate of hot and cold streams, specific heat of hot and cold streams, inlet and outlet temperature of hot streams, inlet and outlet temperature of cold streams. Calculate logarithmal mean temperature difference at MTD. At MTD equal to T1 minus T2 divide ln multiple T1 divide T2. For counter current flow, T1 equal to T hot in minus T cold out. T2 equal to T hot out minus T cold 1. For co-current flow, temperature difference T1 equal to T hot in minus T cold in. Temperature difference T2 equal to T hot out minus T cold out. Calculate Film's coefficients. Allocate hot and cold stream either in inner tube or annular space. General criteria for fluid placement in inner tube is corrosive rate, cooling water, water fluid, and higher pressure streams. Calculate equivalent diameter and flow area for both streams. A equation for inner tube annular space, where di inside pipe inner diameter, do inside pipe outer diameter, d1 outside pipe inner diameter. Calculate velocity, Reynolds numbers, and Prandtl numbers for each streams. For first iteration, a length of double pipe exchanger is assumed and heat transfer coefficient is calculated. Viscosity correction factor due to wall temperature is considered 1. For laminar flow, Reynolds less than 2300, Sandel-Tate equation is used. For transients and turbulent flow, Reynolds greater than 2300, Pettigrew and Pillar equation modified by Janicki can be used, where L for length of double pipe exchanger, nu W viscosity of fluid at wall temperature, Nu Nusselt number. Estimate wall temperature. Wall temperature is calculated as following, where H film coefficient in a pipe, HO film coefficient for annular pipe, T average mean temperature for inner pipe and fluid streams, T average mean temperature for annular fluid streams. Viscosity is calculated for both stream at wall temperature and heat transfer coefficient is multiplied by viscosity correction factor. Overall heat transfer coefficients. Overall heat transfer coefficients is calculated as following, where Ri fouling factor inner pipes, Ro fouling factor for annular pipes, Kt thermal conductivity of tube material. Area and L equation can be calculated area and length of double pipe exchanger. Compare this length with the assumed length if considerable difference is there use these lengths and repeat above steps till there is no change in length calculated. Number of hairpin required is estimated as follows, and hairpin equal to L over 2 multiple length hairpin. Problem example with solution for improvements. Calculate pressure drops. Pressure drop in straight section of pipe is calculated as following: pressure drop in psi, specific gravity of fluid, mass flux. For laminar flow in inner pipe, friction factor can be computed as following: for laminar flow in annular pipe and for turbulent flow in both pipe and annular pipe. Pressure drop due to direction change for laminar flow and for turbulent flow. In last equation, we get the total pressure drops. Effectiveness in heat exchanger and its role in heat transfer. Heat exchangers are critically component in various industrial and engineering applications, facilitating the efficient transfer of thermal energy between two or more fluids. The performance of heat exchanger is predominantly evaluated through its effectiveness, a key parameter that measures how closely the actual heat transfer approaches the minimum possible heat transfer under given conditions. Effectiveness, typically denoted as E, is defined as the ratio of actual heat transfer rate to the maximum possible heat transfer rates. This dimensionless metric reflects the thermal efficiency of heat exchanger and is influenced by factors such as the fluid flow arrangements, counterflow, parallel flow or cross flow, heat transfer surface area, fluid properties, and the presence of polyp or scalings. In the context of heat transfer, improving the effectiveness of a heat exchanger directly enhances its ability to meet thermal performance goals while minimizing energy consumption and operational costs. This generation chemical processing and HVAC system where heat exchanger efficiency impact overall system performance and sustainability. This study explored the significance of heat exchanger effectiveness, its calculation methods, and the parameter influencing it, providing insight into designing and optimizing heat exchanger for superior heat transfer performance.
Assalamualaikum warahmatullahi wabarakatuh. My name Muhammad Fahmi bin Farul Razi, number matrix TD230014. Today I will present about our project which about double tube counterflow heat exchange. So after listen to the previous presentation, the conclusion we get first, efficiency heat transfer. Heat transfer is optimized through the seamless integration of conduction and convection. Harness with a counterflow design the maximizes efficiency. Okay. Second, material selection. So the use of high thermal conductivity material like as copper, aluminium, significantly exchange energy transfer, ensuring optimal heat exchange efficiency. Next, turbulent flow. Turbulent flow exchange convection efficiency by promoting truth mixing, enabling superior heat transfer performance. Next, the critical factor. The performance of the system is profoundly influenced by critical factors such as material selection, flow properties, and operating conditions, all of which work together to determine its overall efficiency and effectiveness. And next, maintenance importance. Regular maintenance is vital to prevent falling and scaling, preserving efficiency, and ensuring the system operates at peak performance. And lastly is the optimizer design. Optimizer design guarantee reliable and efficiency operating, delivering consistent performance and long-term dependability. Okay, so what the recommendation that can be used? Okay, first use high conductivity material. Materials such as the copper or aluminium to minimize thermal resistance, maximizing heat transfer, efficiency, and overall system performance. Second, can be used to optimize flow rate, maintaining a productive flow rate and incorporating design and assignment that promote tubular flow, thriving significantly improving convective transfer efficiency. Third, regular cleaning and maintenance. Uh, Ensure the routine cleaning and proactive maintenance to prevent falling and scaling, safeguard optimal performance and extending the lifespan of the system. The next can be used optimized in solution. Reduce heat loss effectively by implementing high quality insulation, ensuring optimal energy efficiency and sustainable system performance. And lastly, can be used periodic performance evaluation. Conduct regular performance evaluation to identify and resolve any inefficiencies, ensuring consistent reliability and long-term operation excellence. That's all for me. Thank you.
Thank you for your attention, for your ears and your listening. Now, I want from my I'm from my group to give all of you one poem. Okay, that sound like the sun is setting, the day is done. Our through and ideas now we have spoon. With thanks and hope we bid farewell. May success and progress follow you. Alright, thank you. Assalamualaikum.